session of the first has done a lot of work in electricity, but today he's going to talk about two-stage stochastic programming with linear bi-parameterized quadratic recourse. So very interested to hear what
Thank you, Andy. Yeah.
Jong Shi.
Thank you. So I want to thank Andy, Ben. Don't leave.
No.
Yeah. So and Chris and the local organizers for inviting me here to have a chance to sort of reacquaint myself with this field of electricity markets. So I think in the late 1990s, I was at Hopkins and spent about maybe 15-20 years there, and I had a lot of time, very fun time, sort of working with Ben. And so the two of us actually collaborate a lot, and we made some, did some good, I would say reasonable good work in this area of electricity markets, merging mathematics. He's a true engineer, sort of very good mathematical insights, whereas I'm sort of a mathematical optimizer. And so we complement each other very well. And so we actually had some very fruitful collaborations. And I really miss those days, man. So, I appreciate that Andy and Ben sort of invite me here, and then I really learned a lot during the past couple of days. And I surely hope that I can sort of merge into this area again, because there's so many challenging problems. Okay, so, but I'm an optimizer. And also as an optimizer, I like to do things a little bit more rigorous using sort of mathematics. And when I first prepared this talk, actually it was quite mathematical. It was meant for another talk. And so after listening to some of the presentations here, I thought that I probably should introduce a little bit, tone down a little bit about the mathematics, but rather so to give you the essential ideas of what I like to convey. So the title of the talk is quite wordy, but I think that most of you, if not all of you, probably know everything here. Two-stage, I'm sure you understand, right? So you make decisions in the first stage, and then you have a chance to maybe remedy your first stage decisions when some uncertainties arise. So that's a two-stage process, two-stage decision making. Stochastic programming, already we've heard quite a few talks on this topic, and I will give you a sort of a succinct way of looking at sort of my perspective of stochastic programming, especially in light of what I'm going to talk about. Now this one is probably the new thing, bi-parameterized, okay? And even this quadratic part is also kind of new, okay? So I think that the concept of a recourse is sort of very synonymous with the idea of two-stage, when you have a chance to make a recourse decision in the second stage. So that's what a recourse allows you to do. So it's a sort of a very long title, but the only thing that is probably new to most of you, if not all of you, is this notion of bi-parameterized. So I will explain what this means. So this paper actually has 4 authors, and the brains, the architects, okay, the brains behind this talk are the first 2 authors, Junyi, who is there. So Ying is actually hiding behind the scene. She can see us, but we cannot see her. So she's very clever, right? So she can see us, but we cannot see her. But they are really the brains, right? So, and some of you may know Subhajit. He's the expert in stochastic programming. So by having him as a co-author tells you that this is a credible talk, right? So many of you know that I'm not exactly grew up in stochastic programming, but having an expert in the authorship, you can tell that it's a credible talk, that I'm not talking about things about nonsense. Okay, so who am I? So I'm the talker. So my role is to try to convince me that if you want to solve stochastic programming problems, and I know that there are a lot of those stochastic programs in electricity markets, that you should try to think beyond the traditional standard paradigm of singly parameterized problems. Okay, and to start to think a little bit about this idea of bi-parameterized. And so I'm a talker, and I hope that I can convince you that because basically we are now trying to develop the theory, the tools, the methodologies, and we have some initial success. There's a paper that is under review. And so my role is to try to convince you that maybe if you have problems like this, you should not avoid them. You should try to deal with them. Okay? And so the question is how to deal with them. So I'm here to learn, and then I'm hoping that maybe you can, after my talk, you can say, my problems really should be something like this, and then you come and talk to me, and then we can start some collaboration, just like what I've done many years ago with Ben. Right? So I'm going to hope to convince you that this is a paradigm that traditionally has not been looked at in the stochastic programming literature, and I'm trying to present to you that it's probably time for you to think beyond the traditional paradigm. Okay, so that's a 5-minute introduction. Okay, so let me give you this my view of stochastic programming. So what is stochastic programming? It's, of course, traditionally this has been called decision making under uncertainty, dating back to the early days, the initial early days of Danzig. But I want to give it the terminology of it's really a mathematical tool for smart planning under uncertainty, right? So why did I not use the word optimal, right? So if you think about stochastic programming, you certainly is optimizing something, so there must be some optimal property involved. But I avoid using that term, okay? And I don't use, because I like to deal with extension of the traditional paradigm. And so I think that for the kind of problems I'm going to talk about, optimality may not be the goal. Okay, rather instead of optimality, I think that we should be happy to get something that we are happy about. Okay, so I use the word smart planning rather than optimal planning. Okay, so just as a kind of a introduction, so this workshop is about electricity systems of the future, and so I'd like to think, right, that the talk here is really, at least maybe it's not stochastic programming of the future, but at least it opens up a paradigm that you, the practitioner, not only within this electricity market community, but maybe even broadly, that this paradigm of parameterized, bi-parameterized stochastic programming is really something that people using or researching, doing core research in stochastic programming should think about. Okay, and so that's why I say that hopefully this talk is something like opening an opportunity or sort of alerting people's attention to this class of problems by parameterized problem, and hopefully become something that it will continue to develop in the future. So I kind of think of this talk as maybe a very modest version of stochastic programming of the future. Claudia may not agree, but hopefully you will. So, okay. So anyway, so this is the sort of the, okay. So why is it the new paradigm? So traditionally, stochastic programming involves linearity and convexity, right? So you have two-stage problem, which you see. First stage is a linear program, and the recourse function, when you take the recourse action, that's also modeled by a linear program, okay? And so part of the result of that is when you have a recourse function that has in the traditional sense, then this powerful tool of convexity can be applied. However, if you move beyond that, then you really get into this area of very challenging both mathematics and computations, that you actually have non-convexity and non-differentiability And these two properties, they are actually coupled. Okay, so in the optimization literature, you see a lot of people talking about trying to optimize non-smooth functions, but in a way, non-smooth, non-convex, but in a way they are cheating, if I may use the word, because those are what I would call as the easy kind of non-convexity, non-differentiability. But a lot of the problems that the one that I've seen will show here is really where you have, when you have non-convexity, non-differentiability, they couple. You cannot separate them. Okay, and that's what makes the problem hard. So it's from linearity and convexity to couple non-convexity and non-differentiability. So once we faced with non-convex problems, traditionally people shy away from global non-convex problems because they aim for globally optimal solutions. And there's this whole area of global optimization research. And I think that maybe for some problems that those globally optimal solutions are needed, but in a way that, so here's a question for the audience, right? So when you do this kind of apply problems, you have two approaches. One is that you want to build some very simplified models for which you can do a lot of things, and then you sort of study those. Whereas the other approach is that you try to model your problems faithfully, and then you may end up with something very difficult. And so now which one do you want to take, right? And would you rather work with simplified models, or you rather work with realistic, faithful models to the problems that you have on hand? Well, different people may have different answers, right? And I'm sort of the latter kind. Is that I would rather look at, you tell me your full problem, right? And I help you to the extent I can, right? And then if necessary, once I understand your problems well, I'll make simplifications to it. Instead of, so nowadays, I mean, this is something that I'm an optimizer, so I'm allowed to blame people in the optimization community, is that a lot of times we sort of fit the problem to an algorithm. That's bad, right? So you have a set of algorithms, you have a set of tools, and you have this set of problems. I don't want to do that because I don't have the tools, so I would rather fit the problem to the algorithm. That's bad, and that's not. I would rather sort of take the problems, try to sort of model it faithfully, and see what I can do with the ultimate model. So the reason for saying that is because now when I have this kind of non-convexity, non-differentiability present, I'm not hoping for trying to get globally optimal solution. Rather, I want to be able to compute things that are as best as I can, probably not even any kind of optimality properties, but with some kind of stationary property, meaning that they are necessary for any such optimal solutions. And then this is a keyword, right? So I don't want to be able to compute just any kind of stationary solutions, but I use the word stationary solutions with significance. Okay, now this significance here, you can add adjectives. You can say that with statistical significance, that's what happens in machine learning and data science, is that they are happy if you can have some nice statistical properties of the solutions that you can compute, right? Whereas in this community, maybe the significance could be of practical significance, right? So I deliberately left out the word an adjective here, and you can add anything you want. But the key thing is that I'm not aiming for globally solutions, but I'm satisfied if the solution has significance in whatever context that we are interested in. Okay? So, and then once I need to deal with this sort of things, then I need to move from the traditional smooth calculus, okay, for which many of us are trained in, including myself, to non-smooth analysis. Okay? And this actually plays, in fact, I mean, Claudia already mentioned some of this in her work, is that we really need to get comfortable with this kind of non-smooth analysis because, I mean, those are the kind of problems that we need to deal with mathematically, right? Okay, so I hope that this gives you an idea that this sort of the the problem that I'm mentioning here, give you sort of an overview of the thing. Okay, so stage stochastic programming. So now we get a little bit toward the main theme. So I don't think I need to go into too much details of this. Two-stage stochastic programming, there are two-stage decision-making process. And the first stage is that you make a decision today, something happened tomorrow, the uncertainties, and then the decision must be made prior to observation of uncertainties. And there are plenty of this kind of uncertainties, and I don't need to go into details of this. And then the two-stage process give you the option, or give you the recourse to adjust to the realization. Once you observe the uncertainty, you can adjust to that. Very standard. So several years ago, I asked my colleague Subhajit Sen, who is an expert in the area, I asked him, so if you look at optimization, there's so much progress beyond linear programming and convex programming. Okay, so much progress in nonlinear programming. And so why in the computational stochastic programming domain, why do most people restrict themselves to only stochastic linear programs? Okay, so I asked him that question. Because it doesn't make sense, because there's so much progress outside of linear programming in the deterministic case, whereas if you look at just the stochastic programming literature, very much on linear, maybe, well, there's integer, I don't steal very much in integer, but there's very little about even quadratic recourse functions. Why is that? Right, so with exceptions, the bulk of computational two-stage stochastic programming restrict to the setting of linear programming based recourse. And also the outer objective is also linear. More importantly, in the recourse function, the first stage decision variable enters only linearly in the constraints of the recourse function. Okay, so why is that? Why is the first stage decision variable affect only the second stage constraints and not the objective function in the second stage? Why is that? It doesn't make, I'm an outsider, so I'm allowed to make questions, innocent questions, right? And so he doesn't give a lot of, I don't think he gave satisfactory answer. Okay? So why is that? Claudia, why is that? Or Michael?
You can write duals.
No, but linear. Okay.
You wanted an answer.
Okay, good. Okay, yes. Okay. Very good. So you can do a lot of things. You can do a lot of things. But why is it you can do a lot of things, but are you telling me that there are no practical problems that are restricted to that? The answer is no, right? So in a way, there's just the development is very much restricted to this linear programming based stochastic program. And I'm not happy with that, right? So I like to challenge things. So question is why? So the focus of the research is motivated by this question is to look at stochastic program where both the linear cost vector and the right-hand constraint vector in the second stage, they're both affected by the first stage decision variables. Okay? So this is where the bi-parameterization occurs. And then another question is that this is linear programming based, right? So you don't see too much where the recourse function even has a quadratic objective. Why is that? Right? So it has linear objective, but even quadratic objective in the recourse function, you don't see a lot, especially theories there. But in terms of algorithms, for example, there's not a lot. Okay? So that's why we try to meet this kind of challenge, is look at what we call bi-parameterization. So here's the problem. Here's the bi-parameterization. Is that here the uncertainty, this is a first stage variable. It's the constraints is parameterized by the first stage variable uncertainty, but the objective is also parameterized. Okay, so just enough for the introduction, and then I'm done. I'm happy to do that, right? Okay, so this is what I meant by parameterized. Okay, so at least mathematically it's balanced, but the key idea, the key thing is, why do people not look at this kind of bi-parameterization? And Claudia has given a very sound answer. And the key word here is what I said before, is this linearity, convexity to non-convexity and non-differentiability. Once you have your objective function in the second stage parameterized by the first stage decision, immediately you get to a non-convex problem. It's in the first stage variable. Immediately, okay? So if you look at this value function here, when you have x here, even if these are linear, this function here is not convex. And then in the stochastic programming literature, for a lot of reasons, people shy away from looking at non-convex problems. And I think that that's not good. So it's like that, again, this goes back to what I said before. You have a set of tools of convex programming, and you stick to that tools. And I don't think that that's the right way to try to look at real problems, right? Okay, so I can give you a lot of examples. So this has to do with joint pricing. When you start to do where the second stage involves decisions involving pricing as well as production. So this is, so I can give you this other more relevant example. Electricity market is that you have this, you have first the slow response generation in the first stage, and then you have the fast response generation in the second stage. Okay, so this is the first stage production cost, and then you have a value function, and then the first stage. So this is you can have renewable here. So those are uncertainties. Omega 1, omega 2, those are the demand uncertainties. And this is the net, so you produce this much to meet the demand in the first stage, but then you have some residual production that you need to go through in the second stage, right? And so the cost here depends on how much you actually need to produce to meet the unmet demand in the first stage. So this is an example. And then, of course, this is the production, the second stage. Of course, trivial example, just give you a little bit of idea of how the first stage decision variable can enter into the second stage. Right, so very simple. But then naturally, when you, and then previously it has to do with this, this thing with price. Right, so you, in the second stage, if you, in the second stage, if you also need to decide on the price, price is also is a first stage decision. You need to decide the price, but the profit in the second stage, the price will come into the picture. And so the second stage would depend on the first stage. This could be the capacity, for example, but then also the price that you determine in the first stage. And now you end up with the recourse function here being dependent on first stage decision x, as well as the price that is the first stage decision variable. And so again, here immediately you get x and p. Okay, so x and p are the first stage decision variables. Okay, so then we'll move on. And then recently in this paper, they talk about the uncertainty being dependent on the decision. So you have decision dependent on uncertainties. So now your value function actually is integrating over the density functions of the uncertainty, but this density function here is decision dependent. Okay, and so now, and then you have different examples of why you can have a decision dependent uncertainty, mixture of uncertainties and distorted distributions and scale distributions, all first stage decision variable dependent. Okay, so now let's go and talk on maybe 5 minutes of mathematics. Okay, so the specific problem that we address in this paper is this, okay? So you have the first stage cost functions, convex differentiable. We make this nice. Well, we can make this non-convex also, but we want to focus on this part, okay? So we can now see what this linearly bi-parameterized means. It's quadratic recourse because we allow for a quadratic objective in the second stage, and this is convex. So in particular, when this is 0, then you get the second stage as a linear program, but then because of the x here, which traditionally is not in the stochastic programming literature, then it makes it bi-parameterized because you have parameterization here as well parameterization in the constraints. So this is where the bi-parameterization comes in. And the word linearly means that this parameterization is linear in X, and also this constraint here is also linear in X. So if you go back to my very beginning thing, you can have general bi-parameterization, which is something like this, right? But this is, of course, too general for the time being, and so I'm just focusing on this case. Okay, so this is the problem that we're dealing with, and you can forget about this. So this is what the bi-parameterized problem that we're dealing with here. Okay, so the only difference you can say that there are two differences from standard stochastic programming. One is this, okay, because most of the time you don't see the first stage decision variable over here, and then secondly, I allow for a quadratic objective in the second stage. Okay, so how do we deal with this? So I said that this is the value function that you get from this is going to be non-convex, and exactly how non-convex that is. Now this is very interesting. So I want to pose a question to the optimizers, and those who are not optimizers are welcome to answer this question. Okay. So if you look at linear programming books, okay, you look at linear programming books, you see a lot of there's going to be a chapter on parametric linear programming. Okay, and in that chapter, parametric linear programming, they draw some nice convex curves or non-concave curve when you have parameterization in either the constraints or objective. One of the two is going to be convex and the other is going to be concave. But you never find, okay, I can challenge anyone here, you never find in any linear programming book that tells you what the value function of a bi-parameterized linear programming is. So in other words, you have an x in the constraints of a linear program and an x and a parameter in the constraints simultaneously, and you look at that value function as a function of those two parameters. There's nothing in any linear programming book that tells you properties of that value function as a function of the parameter objective, parameter constraints. No, nothing. Why is that? Very fundamental questions, but nothing in the literature. It turns out that if you look at that kind of function is very simple. It's almost convex. It's not convex, but it's difference of convex. Difference you can write as difference of two convex functions. So that brings in this notion. Okay, so before I talk about that, so this is one easy way of dealing with the previous problem. Okay, one easy way of when dealing with this is that you basically, if you have finite scenarios, then you can enumerate all those scenarios and then write down the complete deterministic equivalent. Right? So I write down, I substitute the value function, their probabilities associated with the scenarios. You write down every scenarios, and then you have a variable associated, second stage variable associated with each scenario. So this is the complete deterministic equivalent when you have finite scenarios with known probabilities associated with those scenarios. But what's wrong with this? This is a deterministic, nice quadratic program in X. This is nice quadratic. So what's wrong with this? The thing that is not standard about this is because you have the variable x times y, and this is non-convex. Okay, this is non-convex, and at least so far, the stochastic programming community, they sort of shy away from that. Okay, because immediately you get non-convexity here. Now this is the complete deterministic equivalent, and what we are trying to deal with is that, well, potentially this is very large, non-convex, and quadratic if this is also quadratic, and the question is whether there's alternative approach bypassing this scenario dependent variables y. So you don't need, so for example, Claudia talks about what hedging, the progressive hedging. There's no theory about progressive hedging applied to this problem. No theory, because of non-convexity. Okay, so I mentioned before, let me go to the next next slide here. Oh, I won't go that far. Okay, so I want to talk a little bit about difference of convex. And the thing that I mentioned before is that it turns out that that value function is a difference of convex functions. Okay? So how do we solve difference of convex functions? Very simple. Okay? Very simple. The basic assumption is that we are very comfortable in solving convex problems. Okay? So that's the basic assumption. So convex problem, piece of cake. But then how do you use that piece of cake to deal with non-convex problem? And in particular, how do you deal with this kind of difference of convex thing? Very simple. You're given an iterate, and you take a subgradient of this convex function, and then you linearize it. Okay, so this is basically a linearization. If you have differentiability, this is just a gradient. It's not differentiable, then it's a subgradient. And immediately now you're going to get this kind of, this is a proximal term, and now you're going to get a convex subproblem. And I iterate on this. Okay, yeah, I know. Okay, so yeah, I will stop 5 minutes. So this is the iterative algorithm, and this is the DCA, difference of convex algorithm. So you have something, if you're comfortable solving convex problem, very easy to extend to difference of convex problems. Very easy, just linearizing this. But now the question is, how do I apply this to my bi-parameterized stochastic program? So the good news is that recently, in a very recent paper, we showed that this value function is actually difference of convex. Okay, so you can write it in that form, and so in principle, you could apply it. So what is the bad news? The bad news is that the DC decomposition, writing as G minus H, that's hard. That involves exponential items and things. So in principle, you know there's difference of convex, but in practice, you cannot do it, not using this result. Okay, so we need some alternative approach. Okay, so idea is that, and then the approach that we use is variable. We use sample average. So because we bypass that scenario enumeration approach and use a sample average SAA for those of you, and then use the basic ideas of the DCA. Okay, so we look at 3 cases where the objective function in the second stage is positive definite. This is relatively easy because you can actually write down a difference convex decomposition. This is a hard case. And then especially when Q is positive semi-definite. So think about the case where you have a bi-parameterized linear program. That's actually, is actually quite difficult. And we came up with this notion of generalized critical point. And I want to skip a lot of things and actually go to let me just give you one case. So this is a positive definite case. And this is the sort of the DC decomposition of the value function in the case when the second stage is actually defined by a positive definite quadratic term. And then so if you write it like this, then basically you're going to get a stochastic DC program, DC, not the DC electricity, but rather difference of convex program where you have this is convex, but you have a minus here. So essentially this is very much like standard stochastic program, except that you have this. Actually, in this case, this one is actually pretty nice. It's quadratic. It's a quadratic function, but because but it has a minus sign in front. And so, just give you a little bit of idea. Here's the algorithm, where you actually do some sample and you use the linearization. You use the linearization, and then you add the proximal term. And so, this basically is an algorithm that actually depends or relies on solving convex programs, subprograms. It depends on taking samples, and you can actually prove some results. So this is an easy case, and I will stop here. And then anyone who cares to ask about I also have slides for the PSD case, but then time is up, so I will stop here. I think this is probably a good time to stop. Okay, just give you a little bit of a touch.
So Sarah Ryan is going to.
Okay, please, Sarah. Yeah. Sorry, Sarah, you haven't seen some of these slides.
I haven't seen these slides, but I did see the paper.
Yeah.
And my question after reading the paper, so there's 2 aspects of this model that are new. One is the bi-parameterization, where the decisions affect the objective function in the second stage as well as the constraints. The other is the quadratic term. And the quadratic term seems to be very important for all the proofs of convergence and the algorithm development. So
not in the PSD case. The PD, I've shown the PD case. The PSD case is much more involved. Yeah,
right.
but you can do the PSD case too.
Okay.
Yeah.
So my question is, I didn't see that quadratic term in the dispatch problem that you presented.
Okay, so we have.
And my question is, if
okay.
it's not there, would I want to include that so that I can use the algorithm?
Yeah, so you could. You're right. In the previous in that very simple example, there's really no quadratic part in the recourse function. So you're correct. Okay, so this is just very simple thing, and so I want to refer to. Okay, so this is the. If you look at this, right, so basically you can. This is basically just also a linear objective, but there's no quadratic term. Right. But then we could also deal with this case, except that it's more involved. You need to do some regularization. Okay. So the methodology in the paper does cover this case.
Okay,
but
overall,
it's not.
Maybe it's easier if we do have quadratic.
Correct. Positive definite.
Put them in there.
Positive definite. So for example, just add some small y square thing, then it makes the problem much easier. Okay. But we could also deal with this, except that you need to go through a lot of machinery. That's the second part. If you guys want to stop for another half an hour. No, I'm just yeah, no. Yeah, okay.
This is a very hot topic, DC programming indeed.
Yeah.
There are some work we've done by colleagues. A difficulty that we find is that we get stuck at local minima and they are not meaningful. What do you mean when with significance?
Okay. So I don't have a good answer in the stochastic programming case, but I can tell you what happened in the machine learning context. Okay. So in the area of machine learning, there are a lot of non-convex, non-differentiable problems that you need to solve, and those problems actually come from some so-called population level problem that involves expectation. And what you want to do is, with significance, is in the sense of statistical significance. You want to be able to establish some consistency results of the stationary solution to this problem with some stationary solution of the population level problem. So in the case of stochastic program, what I would be trying to do, this is probably another 5 years project, is that I want to be able to show that the stationary solutions that I get from using this approach would be statistically consistent with the overall problem. That would be one answer of significance. So that's more like a statistical. Okay, so that's more like, so this has the expectation in it, right? And so I want to be able to show that the empirical solutions, stationary solution, will be consistent with a stationary solution of this problem in a statistical sense. But as I said, we started this about 9 months ago. Down the path, we have some results for some machine learning problem. For stochastic program, we don't have results. But the goal is to try to show that the stationary solution that we compute here will be statistically consistent with the original problem. Okay, so that's one interpretation of significance. The other interpretation is that you are the user. You want to solve your problem is of this form, and you want me to be able to give you a solution that you are happy with. So that, of course, is a very non-rigorous, informal kind of significance, but that's what my goal is that I give you something that, so in other words, I start with a realistic model, a faithful model, and I give you something that you're happy with, rather than I start with something that is much simplified, and then I give you a perfect answer in a way I'm less happy with that. I would start with something that is faithful to what is needed, right? And then give you something that you're happy with. That's the sort of the non-rigorous way of thinking about significance. Right? So the more rigorous way is to try to prove some statistical consistency results. Yeah.
So you talk about approximating the X transpose Y using McCormack envelope.
Yes. Okay. In fact, the paper that I quote, actually, which I found out from Jong Shi, This paper here uses exactly that. Okay, well, no, yeah, this paper, they use exactly this, looking at x and y, and then use McCormick group, some global optimization using the Baron code, for example, using the Baron code, right? So you certainly can do that, right? But then the thing is that, I don't know, I mean, we're using a different approach, the SAA approach, and how do the two approaches compare? I have no answer for that. That's the point, yeah. So McCormick is one possibility.
Well,
Yeah.
Thank you so much. So just for clarification, slide 8. So you say that the cost.
Page 8.
Yeah.
Oh.
Yeah. So the recourse cost is quadratic.
This can be 0. If you don't like this Q, you can.
It's not x dependent, right?
No. Okay. Very good question. Okay. If you want this to be x dependent, the answer is I don't know how to do that.
So it's the first step.
Yes, that's the first step. Yes. So I can only do x here and x there. And then if you put an omega here, no, we're at this point.
So the first coefficient is x dependent.
Yeah.
So
Yeah, it's only this part is x dependent. This already is different from standard SP, right? So this part. So if you put an x here, no, I don't know how to do that.
So I'm not optimizer, I'm engineer.
Yeah.
So you had an example of power system, but I didn't get.
No, that's very simple. Don't, okay.
Yeah.
One of the things I'd like to be able to do is to get feedback from people here about whether the idea is in what context will the first stage decision variable should go into objective.
That was exactly my question.
Yeah, so hopefully some of you can give me the answer to that, Ben, maybe. Right? So I'm looking at Ben and others. Right? So because traditionally you only have the first stage decision variable affecting only the constraints. Okay, and so the example tells you that if you also, the second stage involves price, and the price decision is being determined in the first stage. You want to determine price today, but that price variable will not go into the problem until the second stage. Okay, so if that is the case, then you will end up with what I briefly shown here. Right, so you have the x coming in the second stage. Well, no, this is go back to this. Right, so this has to do with shipment and the price you decide in the first stage, and then this is a case where the uncertainty depends on the price, but then the price actually comes into the second stage, and then so this is I think this model actually was more in a logistic kind of supply chain context, but it probably will apply to electricity markets too. Is that you have the joint pricing and shipment. This is shipment, but you can say thing about this as transmission, for example. Is that you have joint pricing and transmission decision to be made in the second stage. And then now you have this first stage variable P and first stage X variable appearing in the second stage.
Michael had a question.
Yeah. Okay.
A very quick question. So you have this essential boundedness assumption on this capital G of omega when in this mixed term.
Oh, okay, yeah, okay. Yeah, okay, so.
The big question is, do you have any further conditions like smallness conditions, or can you take any just essentially bounded?
Just essentially bounded is enough. Just you basically want the random variable. This is just to make the theory complete, that you can divide.
But there's no smallness assumption.
No. We don't need that. We don't need that. Just that you don't want to. If you have unbounded randomness, it's difficult.
No, that I understand.
Yeah.
Just if you make
No, you don't need that. You don't need small. No, you don't need that. Yeah, just essentially bounded is enough.
Okay, thank you.
Yeah.
Any other questions?
Can I ask another one?
One more.
Yeah.
Oh, sorry.
Did I answer your previous question?
Yeah. Well,
Yeah.
So this looks like the linear decision rules or affine policy that the control people they have.
Yeah.
But not on this recourse variable, but on recourse cost.
Yes.
It's kind of the same affine.
Yes, I think that's a very good point. Maybe we should look at that also, how that can be. But I agree that there's some similarity with some linear decision rule things. Yes.
Very good.
Yeah.
Thank you, Jong Shi.
Okay.
Thank you.